Remember some of the big things that came out of yesterday's discussion about Big O, and I'll teach you a couple new things, and then I'll give you a couple practice problems. So try and remember on your own, if I were to say that a method is Big O of n, what exactly does that mean? Go ahead and pretend I am about to call on you, and you need to prepare a sentence. What does your sentence sound like? So two good sentences would be, as the input size gets bigger, the number of steps to finish increases like a linear function, or more succinctly, the number of steps to finish is a linear function of the array length. Just a quick technical note, what I'm describing is actually something slightly different than Big O. It's a thing called Big Theta. Most programmers talk about Big O exactly like this, though, and I'm going to skip the technical part. Okay, and so you could also imagine it like a graph. The input size, which in our case so far has been an array length, as the array length goes up, the number of steps that it takes to complete grows linearly. Okay, so two big ideas came out of last time. One idea was that for some pieces of code, there can be a worst case and a best case. So in this example, we're starting an index at the last element of a list, and we're going backwards through the list as long as there's still more things to check and as long as the elements are positive. So in other words, we're searching backwards through the array until we find a negative number. The reason I was pausing is because I'm realizing this has a small bug. Okay, so a best case, so a lot of people said, yo, the best case is when the array is length 1. But that's not how best cases work. Here's an example of a particular arrangement of numbers that would be a best case for a length 3 array. Here's a best case for a length 8 array. In both cases, you have a negative number as the first thing that we check, which is the last element in the list. So you could imagine a best case where your array length was 1 billion. The best case would be a negative number is the last thing in the array. So best case isn't about having a small array size. A best case is about the particular values that would lead any array size to run the fastest. Conversely, we could have some worst cases. So here's a worst case for a length 3 and a worst case for a length 8. And they're worst cases because there is no negative number. And so this while loop would have to visit every single element of the list. And that's why the worst case increases linearly. It's because if you have to visit every single thing in the list, you know you have to take that many steps. So if there's n elements in the list, you would have to take n steps. Okay, so it's possible to have a best case and a worst case, but a big takeaway is there's a best case and a worst case for each input length, assuming that you have code where these are different. Sometimes you might have code where it's not possible to have different examples of each input size, and in that case, the best and the worst would be the same. Okay, so the second big idea to come out of yesterday was if you want to, it's tempting to look at the loops. It's tempting to look at two nested loops and say, oh, that must be n squared. But don't look at the number of loops. Instead, you need to think about the idea of Big O, which is how does the number of steps grow as the input size grows? So don't look at loops. Think about what happens as your array gets larger. So right now, pause the video and decide what do you think is the Big O of this left-hand method, and what is the Big O of this right-hand method? Hopefully you said that the left-hand method is constant time, and the reason it's constant is because we're always looping 100 times 100, which is 10,000. So this print statement is going to run 10,000 times no matter what. I make the array length 500, this is going to loop 10,000 times. I make the array length 1 billion, this is going to loop 10,000 times. So that's why it's constant. It's because the number of times that this loops doesn't have anything to do with the array length. This one, on the other hand, the inner loop is going to loop n times. The outer loop loops n times. And so that was the n squared example that we had from yesterday. All right, so it's time to delve into some new territory. Think about this one. So on the left-hand side, we've got the same n squared example from before. What about this side? It's possible it's n squared. It's possible it's something less than n squared. Decide what you think. Pause the video. So you could think about this in a couple of different ways. One idea is to think about how many times will each loop repeat. Oh, we're in the wrong one. Where are we? Hold on. Okay, let's think about how many times each loop will repeat. So we're only looping up to the end of the first half of the elements. So rather than looping n times, so far we're looping n over 2 times. But even then, we're only visiting 1/4 of the elements. So rather than looping over half of the elements, we're looping over 1/4 of that half. So the inner loop is looping over 1/8 of the length of the array. And then the outer loop is also looping over 1/8 the length of the array. And so if you want to know how many times how many steps will this inner print statement run for, the answer is 1/64th times the square of the length of the array. So this is still big O of n squared because we ignore this coefficient in the front. A different and kind of looser way of thinking about answering this kind of question is asking yourself, does each loop depend on the length of the array for how many times it's going to repeat? And so if the loop depends on the length of the array at all, it's going to run proportional to the array size. And so you can say this is going to run proportional to n, this is going to run proportional to n, therefore it's going to be proportional to n squared. So you can also think about it kind of more loosely that way. Let's try another one. So here on the left is big O of n squared. Here on the right is the conventional way of looping over all pairs of elements in an array. So I visits every element, but then j only visits elements larger than I, because we initialize to be 1 larger than I. So take a minute and decide what you think this one is, and the most important is why you think your answer. Okay, so this one is also big O of n squared. There are 2 ways you could think about it, probably more than 2 ways. We can't do that trick where we say, oh, the outer loop is looping n times and the inner loop is looping like 1/2 n times, because the number of times the inner loop runs changes with every outer loop. So you can't do a straight multiplication like that. If you want to use the informal rule I just told you, even though the inner loop changes the amount of times it runs, the number of times it repeats still depends on the array length. So if you've got something that depends on the array length times another thing that depends on the array length, that's still going to be n squared. There's another nice way of thinking about it, though. Let's imagine what's going to happen if you have an array length that's 5, all right? So let's say this is our length 5 array. We've already decided that this outer loop is going to loop 5 times. So let's visually represent that. Okay, so the outer loop, when I equals 0, let's shade in the locations that actually get visited inside the inner loop. So we'll initialize, here's the array indices. So when I is 0, we initialize j to 1, and we visit these elements. Then in the next iteration of the outer loop, when I is 1, we initialize j to 2, and we visit these elements. Then when I is 2, j is 3, and we visit these elements. And when I is 3, j is 4. And when I is 4, j gets initialized to 5, and then it immediately fails this check because 5 is not smaller than 5, and so we never run the inner loop at all. Okay, so here's something to notice. Something to notice is this is n elements. This is n elements. So the area of the whole thing is n squared, and this is approximately half of the area. And you can remember the whole test is what happens to the number of steps as the array size increases. So you could imagine increasing the array size to size 100, for example. In that case, the outer loop is going to run 100 times. When I is 0, j initializes to be 1, and you're going to loop over all the elements except that first element. And then when I is 1, you're going to loop over all the elements except the first 2 elements, and so on. So you're still going to loop over roughly half the area. Only this time the area isn't 5 times 5 is 25, but 100 times 100 is 10,000. But hopefully you can kind of visually see this geometric argument that the number of things that we visit is going to scale as the square of the array length, because you can represent it as this area. One last way to think about it, if you all remember pre-calculus, so let's write down the exact expression for how many elements we visit. So here we're visiting 4 elements. Here we're visiting 3 elements. Here we're visiting 2 elements. Here we're visiting 1 element. And then we're visiting 0 elements. So you add them all up, and that's 10 elements. You might notice this 4 plus 3 plus 2 plus 1 pattern. There's a name for this that you learned in pre-calculus. It is an arithmetic series. And if you want to write down what is 1 plus 2 plus 3 all the way up to this n minus 1, because if the array length is 5, we only go up to 5 minus 1 is 4. So if you want to write the expression for this, one way to think about it is let's add all the things in pairs. So 1 plus n minus 1 is n. 2 plus, this must be n minus 2 is another n, and so on. So we have a whole bunch of n's. How many of those n's do we have? Well, there were n total elements here. Nope, that's not right. We have n minus 1 elements, because with the array length 5, we would have covered 1, 2, 3, 4 of them to get down to 1. So we have the number n, and we have it for like 1/2 of the n minus 1 times, because we have n minus 1 total elements, but we're dividing them in pairs. So this is an expression for how you would calculate the sum of that arithmetic series, and you'll notice that this is proportional to n squared. So that's another reason why it's big O of n squared. I think at the end of the day, though, it's probably easiest just to think, is each of these loops dependent on the length of the array? All right, last example. Here's a thing that you maybe didn't know was possible. Think about why is this method different than the first one? So in the first one, each loop loops over the length of the one array. Here we have 2 arrays. So array 1 is going to loop array 1 length times. Array j is going to run array 2 length times. So how would you notate the big O here? If the number of steps your program requires depends on 2 different things that can grow, you just give names to each of those things. So here I would say, let's say array 1 length, I'm going to call that one n. Array 2 length, I'm going to name as m. And the big O is just m times n. And that's totally normal. This is a totally reasonable thing that you can write because it correctly expresses how the number of steps grows. If I keep array length 1 constant and I make array length 2 larger, then it's going to grow just like a linear function for array length 2, because n is going to be held constant and m is going to be like a linear term. However, if array length 1 and array length 2 are both growing together, then it acts more like a quadratic because I'm multiplying 2 things. To contrast, in this case, we still have 2 different inputs that could grow in size, but now the loops aren't nested. So this first loop is going to run n times, the second loop runs m times. So you would notate this as big O of m plus n. All right, so the point of this was just to show you that this is possible. So you can have whatever expression correctly describes the number of steps on the inside here. All right, it has come time, nope, not that. It's come time for you to try the problem set. The sub should hand it out to you. Give it a quick try and then watch the solution walkthrough video.